Hi everyone, my talk is based on a paper that I've been working on with my supervisors about optimizing coral aquaculture production. So coral reefs are the ocean's most biologically rich ecosystem, but they're also one of the most climate sensitive on the planet. And the world's coral reefs are declining. So we need to maintain and restore these reefs through active restoration to get immediate results. So existing restoration approaches are not scalable. You can see here in this image the number of people required to restore this small reef. So now degradation is happening at a much larger scale and we need a change in approach. So a global reef restoration sector is emerging, but new restoration methods are being developed and tested, which create a new and significant logistics problem. So here we're looking at coral aquaculture. This is used to grow corals in a controlled environment, transport them and plant them in the wild. So for any given project, we can immediately ask, how many of these facilities do we need? How big do they need to be? Where should they be? And how long do we grow coral before planting them? And each of these decisions will affect whether production is optimal. So these are basically the questions that we set out to answer. So the Australian government is funding a large-scale project to restore the Great Barrier Reef. And the Great Barrier Reef covers over 300,000 square kilometres, making up about 10% of the world's reefs. But we simply don't have the resources to restore the whole reef. So we have petitioned the reef into a subset of 50 reefs to restore. So already we can ask which 50 reefs to restore, and each different subset of 50 reefs will affect the solution, which I'll go into a bit more detail later. So the mathematical model that we've created has an objective to minimize costs for the project. So the costs we consider are in green, and these include the fixed cost to set up a facility, the variable cost to set up a facility, the operating costs, and the transport costs for coral from each facility to reef. And then the decisions we make are in red. So these include whether or not to open a facility, how much coral to transport from each facility to reef, how long to keep coral in a facility, and how many trips to make between each facility and reef. And there are a few constraints, including ship capacity, how many trips to make, the proportion of coral that survive, and about facility production constraints. So here we consider, why would we keep coral longer in a facility rather than getting them out quicker? And when is the optimal time to deploy them and start producing a new batch of coral? So some proportion of coral deployed will survive. And these functions relate the residence time in a facility on the horizontal x-axis to the chance of survival in the wild on the y-axis. So we don't know how the coral will behave based on their residence time, and we explore 4 different forms. So 3 of these forms are increasing over the residence time, and one here in the bottom right is a gamma curve, which represents coral that become domesticated and then reliant on lab conditions and past a certain point behave less survive in the wild. So decisions about residence time in a facility affect coral survival rates. And if more coral survive, we don't need to produce as much to meet restoration demands. And therefore we can save money by building and running smaller facilities. So there's a trade-off here between producing more volume and having quicker batches, or coral having more chance of survival and lower production requirements. So we ran 100 different subsets of 50 reefs across the Great Barrier Reef, and you can see the confidence in cans as a solution. It appeared in 100% of optimal solutions as a facility location. And this was also true when we broke down facilities, optimal solutions into the number of facilities where it was also favored. So if cans is established, locations close to cans are largely redundant. And you can see a trend in optimal facility increases as the distance from cans increases. So in reality, it's a surprising result to show low confidence in Townsville as an optimal location, because Townsville is a regional centre. So then we look at adjusting cost parameters to assess the benefits of setting up facilities in Townsville. So here we've scaled each cost parameter by an integer power of 2. So the base case is this top row, which is our initial assumption and which we've used to compare against. And then we've included solutions outside of a threshold with the 6 optimal facilities. So you can see an increase in all of these variable cost parameters. An increase results in an increase in the optimal number of solutions. And this is because when any of these variable parameters increases, it results in a relative decrease of fixed capital, and that results in an increased number of facilities. And we can also see an insensitivity of the optimal facility number and location to changes in variable capital and variable operational costs. So this insensitivity is shown here by a huge range between, this is 2 to the 11 and 2 to the -1. And for here, it's 2 to the 10 and 2 to the -1. So that's a huge range of numbers where within that range, the optimal number of facilities stays at 6, it doesn't change. And that highlights the unimportance of obtaining certainty of these parameters for decision makers. So basically our contribution here is the method, which is transferable to other parameters and data sets. And this can be extended to other products whose value is affected by its age pre-deployment. And this is things like mariculture and aquaculture of other fish and marine species, as well as livestock agriculture, nursing and harvesting other plants, crops and plantations. And the main findings for decision makers are the long-term strategic decisions, which are dependent on deployment and fixed facility setup costs, and also that coral survival characteristics drive tactical decisions of facility sizing, and also optimal residence time for corals. And the large variance in these results highlight the value of obtaining certainty for these survival characteristics. Yeah, so consideration of dual mode transport could be included, as well as staggered facility expansion and increased clarity in coral survival. Thanks.